Okay, we're back. We're talking about work, and as you remember, work is the product of the work done by a force, I should say, is the product of that force multiplied by the displacement of the object, multiplied by the cosine of the angle between those two vectors, the force and the displacement. And what work shows us is it shows us how much energy was transferred either between two different objects or between one type of energy to another. Our next question: how much work is done by you if you carry a 20 kilogram box 30 meters at a constant velocity? So when it says by you, it's kind of implying that we're talking about by the applied force, okay, the force that you're actually putting on this object. It doesn't tell us how big the applied force is, so maybe we should draw a free body diagram for this. Here's our box, here's our axis. We have the force of gravity going down, and we have the normal force going up. And I want to redirect your attention back to the question. At a constant velocity, you're carrying this box. So imagine you've got a box in your hands. It's very heavy. It's 20 kilograms. It's pretty heavy. And you're carrying this box around, okay? And you're doing so at a constant velocity, meaning you're moving at the same speed and in the same direction the whole time. We know that constant velocity means no acceleration, which means no net force in that direction. So let's think about it like this. Do we need an applied force if we're already moving at a constant velocity? The answer is no, because if you were to draw an applied force in, let's say it points to the right, there's no reason that you would draw a force of friction backwards because you're carrying the box. It's not like the box is sliding over something. You're carrying it to the right. There's no force to resist that. That would cause an acceleration, but you're already being told that there is no acceleration. In this case, there is no applied force. So if I want to find the work done by the applied force, that's got to be equal to the applied force times the displacement times the cosine of theta. Well, if there is no applied force, that means the work done by the applied force is 0 joules. No energy was transferred by that force. So you might be saying, okay, well, maybe we're not talking about the applied force here. Maybe we're talking about the normal force or the force of gravity. Well, think about it like this. Those forces are vertical, either vertical up or vertical down. The displacement, if you're carrying something, it doesn't say you're lifting it up or putting it down, you're just carrying it. The displacement's got to be to the right or to the left, however you want to write it. Well, those forces, Fn and Fg, would be perpendicular to D, which means there's a 90-degree angle between those vectors. And wouldn't you know it, the cosine of 90 degrees is 0. So that would mean there's no work done by those forces either. So for the applied force, let me go back to that for just 1 second. Once the box is at constant V, no Fa needed to keep it moving. So the applied force does no work because it doesn't exist in this case. The work done by the normal force would be the normal force times the displacement times the cosine of theta. This would end up being Fn times d times, I'm not even going to bother trying to figure out what the normal force or the displacement are. I just know that this would be the cosine of 90 degrees. That's 0. So the work done by the normal force is 0 joules. And the same thing happens for the force of gravity. So we really have 2 takeaways from this question here. The first is that if the force doesn't exist, it obviously can't do work. It can't transfer energy. The other is that if the force and the displacement are at a 90-degree angle, no work is done. Now, you might say, wait a second. Carrying something definitely requires us to do some work. You get tired after you carry something. And that's true, but that's thinking of work in the terms that we're not thinking of work in, okay? We're not thinking of work as, do you get tired or not? We're thinking of work as in, is energy transferred from some object to some other object or between different types of energy? And the answer here is that no, it is not. Now, the reason you end up feeling tired in this case is because your muscles, in order to hold that box as you move, are contracting and expanding a little bit, and that actually causes you to feel tired. So you could almost say that your muscles are kind of like doing work on themselves, almost, but you're not adding any energy to that box. That's the key here. You are not transferring energy to or from that box. So no work is being done in this situation. That's very misleading. People like to think that if you carry something, you're doing work. That's not the case. Okay. Next example. How much work is done by gravity if you, with a mass of 70 kilograms, ascend a widening staircase that is 6 meters high at a constant speed? Okay. We're looking for the work done by gravity. Work done by gravity equals the force of gravity times the displacement times the cosine of theta. Now, the force of gravity, as we know, points downward. But if you're going up a winding staircase, your displacement is upward. Before we even get into calculating F, G, and D, because those are simple, what's the angle between these two forces? They're in exactly opposite directions. If you set 180 degrees, you're right. The angle between these two forces is 180 degrees. If I were to line these up, if I were to drag this one over here, then I would have 180 degrees between the two vectors. They're not both forces, they're vectors. So I can plug in mgd, because I know FG is mgd cosine theta. And I'm going to plug in 70 kilograms, 9.81 meters per second squared. The displacement is 6 meters, and we're dealing with the cosine of 180 degrees. Now let's think about what that is. 180 degrees cosine, that's -1. So notice that this time, when we get the work done, there we go. When we get the work done, we get a negative answer. The work done by gravity is 4,120.2 joules. Here's what I want you to think about. What does that mean for negative work? Well, think about when you jumped down from that ledge. When you jumped down, you weren't in motion to begin with, and then by the time you got to this is the last example on the first video. When you jumped down from that ledge, originally you weren't moving, and then you were. It's like you gained some energy, okay? Remember, one way that something can have energy, or what energy really means, is the ability of something to move or potentially move. So in that case, when you were jumping down, there was a positive amount of work done, and it seems like you had more energy at the end than before. So positive work means energy is going into an object. Well, what would that mean for negative work? That must mean energy is coming out of an object. What happens when you go upstairs? You feel tired afterwards, don't you? Energy was taken from you. In this case, really, energy is taken from you and it's transformed into a different type, but that negative means that energy was being, I don't really want to say lost, but energy was going out of that object, or it was going out from whatever it was, whatever type it was before. Okay, so you can have a negative amount of work done. It means that energy is flowing out of something. So if the force and the displacement are at a 180 degree angle, then the work done by that force is negative. Energy flows out. Okay, we have an outward flow of energy. So there's 3 angles that you should know about. 0 degrees, okay, that's nice and simple. That's positive work. It's actually the maximum amount of work that can be done for that force and that displacement. If the force and displacement are 90 degrees apart, no work is done. And if they're 180 degrees apart, negative work is done. Matter of fact, it's the maximum amount of negative work done for that particular force and displacement. So those 3 you should have in your head. Now, what if you have something that's not in those directions? How much work is done by the applied force if a 30 kilogram child pulls a 15 kilogram wagon a distance of 7 meters with a force of 20 newtons at an angle of 30 degrees? Here's my applied force. Here's the displacement. When you pull a wagon, you're presumably pulling it horizontally. Okay? Now, what's the angle between the applied force and the displacement? Well, displacement is to the right. This vector is also to the right, and that's a 30-degree angle. That's what theta is in this case. So, the work done by the applied force is equal to Fa times the displacement times the cosine of the angle between the applied force and the displacement. The applied force was 20 newtons. The displacement was 7 meters times the cosine of 30 degrees, because 30 is the angle between that force and the displacement. 20 times 7 times cosine of 30 equals 121.24 joules. So here's another thing to notice. Okay, here's how much energy was transferred, the amount of work that was done. Remember, work is just a transfer in energy. 121.24 joules. If the applied force had been in the exact same direction as the displacement, then we would have just done 20 times 7 times cosine of 0, which would have given us 140. So notice that as the angle, as the angle between the force and the displacement grows away from 0, as they become kind of less and less aligned, the amount of work done decreases. The amount of work done decreases. If they were 90 degrees apart, we'd have no work being done. The reason they decrease is because less energy is being transferred. The force and the displacement are increasingly not aligned. Okay? Now, I used to do this a slightly different way, and I'm looking back on it. I don't really know why I was doing it this way. So we can actually cross off this note. We're going to write it slightly differently. We're going to write it like this. If F and D are at some other angle than 0 degrees, 90 degrees, or 180 degrees, use that as theta in equation and solve. In parentheses, will give non-maximum and actually non-minimum amount of work done. So it just won't be the maximum amount of work done, okay, or the minimum, really, for that matter, okay? But you don't have to treat it really any differently. The old way I used to do it is I used to have people split this into components, and then we would see that the x component is what does all the work, the y component does no work, but that seems way too complicated, okay? It's true, but it just seems like we're overcomplicating things. Let's go to the back where we have an example. And then we'll be done with talking just about work, and we'll get into talking about other types of energy. All right, there we go. A 10-kilogram crate is being pushed across a rough surface at a constant velocity. So notice that they already tell us rough surface, 10-kilogram crate, constant velocity means the acceleration is 0 meters per second. The woman pushing the crate exerts a force of 60 newtons on the crate. That's the applied force, and pushes it for 20 meters, displacement. Coefficient of friction between the crate and the surface is 0.61. Coefficient of friction is symbolized by mu. First, draw a free body diagram for the crate and write the net force equations for both directions. Simple enough, this is just forces review. So here's our crate. Oh, need my axis, xy. We have a force of gravity down. Applied force because the woman is pushing it. We're told rough surface, and we have a coefficient of friction, so that implies there must be a force of friction, and we have a normal force. Our very standard free body diagram. Net force equations, F net x equals Fa minus Ff equals max. However, they told us that this is moving at constant velocity, so the acceleration must be 0. and that implies to us that the applied force is equal to the force of friction. Okay, if we just add the force of friction over to 0, we get them on equal or opposite sides. F net y is Fn minus Fg equals may. The crate is probably not accelerating up or down. We can assume that that acceleration is 0. Therefore, Fn equals Fg. We kind of already answered B. What is the acceleration of the crate? We already said that it's moving at a constant velocity. It's also not starting to accelerate up or down. So, since we have constant velocity, constant horizontal velocity, means no horizontal acceleration. And there's no vertical acceleration either. Okay, so that helps. What is the work done by the applied force? Work done by the applied force, WA, equals FA times D times the cosine of theta. Now, I probably should mention that the displacement, the crate is getting pushed probably in the direction the woman is pushing it. So there's our displacement. Remember, don't draw the displacement on here. It's not part of the free body diagram. It's just something we're drawing in addition. So we have the applied force is 60 newtons. The displacement of the crate from start to finish is 20 meters times the cosine of 0 degrees, since the applied force and the displacement are in the same direction. Don't forget the degree sign. The cosine of 0, as you know, is 1. Therefore, the work done by the applied force is 1,200 newtons. 60 times 20 is 1,200, or excuse me, joules, not newtons. Now that means that the applied force is putting energy into the crate. Okay, energy is flowing into the crate. Think about what friction does. Friction tries to rob objects of their speed. So it kind of makes sense that friction should take work away. The force of friction should do maybe negative work, take energy away from the crate. What is the work done by the force of friction? Well, we can see that the force of friction is in the opposite direction as the displacement. So we already know that the cosine, that the angle we're going to plug in is 180 degrees. But until we get there, the work done equals FF times D times the cosine of theta. Now, how are we going to figure out what the force of friction is? Force of friction is mu times Fn. That's the equation for it. And we know from up here that Fn equals Fg. Matter of fact, we can even write Fn equals mg. We'll write that now. Mu mg d cosine theta. So mu is 0.61. M, the mass of this crate, is 10 kilograms. G, 9.81 meters per second squared. D, 20 meters. And the cosine of 180 degrees. Cosine of 180 is negative 1. So this is just going to make our answer negative. Okay, so we have 0.61 times 10 times 9.81 times 20 times negative 1. And with some rounding involved, because obviously, well, I shouldn't say obviously, but if we if I'd gone out to more digits on my coefficient of friction, this would have been a little bit better. But look at that number. It's really close to what? We rounded a little bit. It's really close to negative 1,200 joules. That's the work done by the force of friction. So the applied force puts energy into the crate. The force of friction takes that energy out. E, what is the net work or total work done on the box? A couple different ways you could do this. You could find the work done by the net force. In other words, W net equals F net times D times cosine of theta. In that case, the net force we know is 0 because the acceleration is 0. Or you can see for yourself that the work done by the applied force plus the work done by the force of friction equals the net amount of work done. that would be 1200 joules plus a negative 1200 joules. The net work is 0. There's no net energy flow into or out of this crate because of how this is set up. Okay? There's equal amounts of energy flowing in and out. And again, we're going to talk in the next few videos about the different types of energy, so this will make a little bit more sense. Right now, I just need you thinking of energy as something that if an object or system has energy, that means that it can move or has the potential to move in the future. So, the total or net amount of work done on an object may be found by finding the work done by each force and add them together. And what the net work does is it shows the total energy flow into or out of the system. Okay? The total energy flow into or out of the system. Is the system gaining in energy or is it losing energy? That's what the net work will show you, and that's something you can calculate. That's it for work. In our next two videos, we're going to talk about about 3 of the main different types of energy. There's 4 types of energy we'll discuss in this particular unit. We're going to talk about 3 of them in the next 2 videos, and we'll talk about the 4th after that. Okay? I'll talk to you later.